Welcome to the deep dive. Today, you're joining us as we plunge into, well, one of the most mind-bending mysteries of the cosmos, dark matter.
It really is something else.
Think about this for a moment. All the stars, the galaxies, everything that you can see, all the stuff we know about, it makes up only, what, about 5% of the universe? According to our best models, anyway.
That's the staggering part, yeah.
Yeah.
Just 5%.
So, what is this dark matter? It supposedly makes up about a quarter of the entire universe, and yet it remains completely invisible to us. That's the incredible question we're going to explore with you today on Cosmic Origins Revealed.
It truly is a profound puzzle for everyone, really. You can't see it, you can't touch it, and yet the evidence that it's out there shaping the universe, it's surprisingly strong.
Okay.
When scientists look out at the cosmos, they observe things happening that simply don't make sense if you only account for the gravity produced by the matter we can see.
Right, the visible stuff.
Exactly. This has led cosmologists to propose that there must be another form of matter present, one that interacts through gravity, but otherwise, stays hidden from view.
Okay, let's dive into this evidence together then. Where did this incredible idea of invisible matter even come from? It's not like someone just tripped over some shadow in space, right?
No, not quite like that. The evidence comes from meticulously observing how visible matter behaves, but on a really grand scale across the universe.
Okay.
One of the earliest and most compelling clues came from studying how galaxies spin. Now, you might expect that as stars get further away from the center of a galaxy, their orbital speeds would decrease, right?
Yeah, like planets orbiting our sun, the outer planets move slower. That makes perfect sense.
Precisely. That's what Newton's laws predict based on the visible mass. However, what astronomers actually discovered, and this was thanks in large part to the groundbreaking work of Vera Rubin back in the 1960s,
Ah, yes, I've heard her name mentioned.
was that the stars in the outer regions of galaxies don't slow down like you'd expect. In fact, their rotation speeds stay constant, or sometimes even increase slightly.
Wait, really?
Constant.
Yeah. It's as if the galaxy has far more mass distributed throughout it than what, meets the eye. Imagine for a moment, like a spinning record player. If all the weight was just in the center label, the outer edge shouldn't be spinning as fast as the parts closer in, right? But that's kind of what we were seeing in galaxies. It was a real cosmic head-scratcher.
Wow, that's a bizarre image. So it's like there's some kind of invisible anchor out there, just keeping those outer stars whirling around at high speeds.
That's a really good way to put it, actually. An invisible anchor. This unseen mass, which we now call dark matter, must be spread throughout the galaxy, even way out in its halo, to exert enough gravitational pull to explain those unexpectedly high rotation speeds.
And it's not just individual galaxies acting strangely, is it? I seem to recall hearing that entire clusters of galaxies behave, well, peculiarly too. That's another crucial piece of the puzzle, definitely. When scientists examine these massive collections of galaxies, these galaxy clusters,
Right.
they find that the total amount of visible matter, stars, gas, dust, it just isn't enough to hold these clusters together gravitationally.
So they should be flying apart.
Based on the gravity from what we see, yeah, they should be. But they aren't. They're stable. This strongly suggests there's a significant amount of extra non-luminous mass within these clusters, acting as a kind of invisible glue.
Invisible glue, I like that.
And large-scale surveys of these clusters, and even larger superclusters, they just keep reinforcing this idea.
Okay, so galaxies spinning too fast, clusters held together by invisible glue. What about this gravitational lensing thing I've heard about? That sounds almost like science fiction.
It does sound amazing, doesn't it?
Yeah.
Gravitational lensing is rooted in Einstein's theory of general relativity.
Right, space-time warping.
Exactly. Massive objects warp the fabric of space-time around them. And because of that, they bend the path of light that passes nearby. So what scientists observed is that light from very distant galaxies is often bent, distorted, magnified as it passes by closer, massive objects like galaxy clusters. And the key thing is the amount of bending we see is often far greater than what you'd expect just from the visible mass of the cluster.
Ah, so again, there's more gravity than meets the eye.
Precisely. It points towards the presence of unseen mass, dark matter, amplifying the gravitational field and acting like a giant invisible lens in space.
Okay, so the evidence is really piling up. Galaxies spinning too fast, galaxy clusters mysteriously bound, light bending more than it should. If this dark matter isn't made of ordinary stuff like stars or gas that we just, can't see, What in the universe could it actually be? Have scientists come up with any solid ideas?
Well, initially the hypotheses did revolve around normal matter that was just hard to spot.
Like what?
Things like massive collapsed stars, maybe huge clouds of hydrogen gas, or very faint dwarf stars. Then the concept of MACHOs emerged, massive astrophysical compact halo objects.
Nachos, okay. Catchy name.
It is. And this category included things like old dim stars, maybe non-luminous black holes or brown dwarfs. Those objects not quite massive enough to ignite into stars. These were all possibilities for the unseen mass.
And how did scientists try to hunt down these MACHOs? Sounds like searching for needles in a cosmic haystack.
It was tricky. A very clever technique called microlensing was developed.
Microlensing.
Yeah. The idea is, if a MACHO were to pass directly between us and a distant background star, its gravity could briefly bend and magnify that star's light.
Ah, like a tiny temporary lens.
Exactly. It would cause the background star to appear brighter for a short period. Several dedicated experiments were set up to just stare at millions of stars, looking for these brief brightenings.
Did they find any?
They did observe some microlensing events, yeah, which was exciting.
Right.
But the data suggests that MACHOs, while they likely exist, probably only account for a small fraction, maybe less than 10% of the total dark matter needed.
So not nearly enough hidden stars and black holes to solve the mystery.
Doesn't look like it, no.
What about those vast clouds of gas or dust you mentioned? Could it just be a massive invisible cosmic dust bunny?
Yeah, a cosmic dust bunny. That's an image. Well, cold gas and dust clouds were also considered. But there are problems there, too.
Such as?
For one, under the conditions in galaxies, cold gas tends to heat up eventually and emit radiation, like radio waves or infrared, which we should be able to detect if there was enough of it.
Okay.
And maybe more importantly, even if you had enormous amounts of cold gas or dust, it just wouldn't provide nearly enough gravitational pull to explain the rotation curves or the cluster dynamics. Plus, that much dust would block starlight or re-emit infrared light in ways we just don't see.
Right, so these more ordinary matter candidates seem to fall short.
They do.
Yeah.
Which really pushed scientists towards more exotic possibilities.
Okay, so we've ruled out a lot of the usual suspects. That leads us to the really strange stuff, doesn't it? These exotic particles I've heard whispers about.
Precisely. The leading theory now really focuses on non-baryonic elementary particles.
Non-baryonic, meaning not made of protons and neutrons like us and everything we see.
Exactly. These are particles that are fundamentally different, and crucially, they likely don't interact through the electromagnetic force.
Which means?
Which means they don't interact with light,
Yeah.
they don't absorb it, they don't emit it, they don't reflect it. That's why they're dark. And they probably don't interact via the strong nuclear force either. It's a totally different kind of stuff.
Okay, this is where things start to get a little theoretical for me. Can you give me an example of a particle like that, something we actually know exists?
Sure. Neutrinos are a known type of elementary particle that fits some of these criteria. They interact very, very weakly with ordinary matter, and they have no electric charge.
Ah, neutrinos, I've heard of them. Ghost particles.
That's right. For a while, they were considered a possible candidate, or at least part of the dark matter. However, scientists now know their total mass, all the neutrinos in the universe combined, is just far too small.
Not enough gravitational heft.
Not nearly enough. They probably make up less than 0.5% of the needed dark matter. Plus, there's another issue. They're hot dark matter.
Hot, as in fast-moving.
Extremely fast, yeah, close to the speed of light, especially in the early universe. If dark matter were mostly hot like neutrinos, it would have tended to smooth out small density fluctuations. This means the largest structures in the universe, like huge superclusters, would have formed first, and smaller things like galaxies would form later by fragmentation, a top-down process.
But that's not what we see.
No. Observations strongly suggest galaxies formed relatively early and then clustered together hierarchically, a bottom-up formation. Hot dark matter just doesn't fit that picture well.
Okay, so neutrinos are too light and too fast to be the main ingredient. That brings us to these other, more mysterious particles with those interesting names.
Indeed. Among the most promising non-baryonic candidates are
WIMPs.
weakly interacting massive particles. That's the one. These are hypothetical particles that, well, like that name says, interact very weakly with normal matter, but are thought to be relatively massive, much heavier than protons, perhaps.
And that massiveness is key.
It is. Being massive means they would have been moving slowly in the early universe, making them cold dark matter. And that fits beautifully with the observed bottom-up hierarchical structure formation we see.
Okay, so WIMPs fit the structure formation picture. How are scientists actually looking for them if they're weakly interacting?
It's incredibly challenging. There's a global hunt underway using direct detection experiments. These are often located deep underground to shield them from cosmic rays and other background noise.
Underground, right? Like in mines.
Exactly. Experiments like Cosinus and Xenon 1T and others, they use large detectors made of special materials, like liquid xenon or germanium crystals.
And they just wait.
They wait for the incredibly rare event of a WIMP passing through the Earth and happening to bump into the nucleus of an atom inside their detector. It would cause a tiny recoil, depositing a minuscule amount of energy. Detecting that faint signal is the goal. The CREST experiment in Italy, for example, uses supercooled crystals near absolute zero to detect both the tiny bit of heat and the faint flash of light from a potential WIMP interaction.
Trying to catch these ghost particles bumping into atoms deep underground, that sounds unbelievably difficult.
It is. Decades of searching and still no definitive detection, though they keep getting more sensitive.
What are some of the other exotic possibilities then, if WIMPs haven't shown up yet?
Well, another fascinating set of possibilities involves axions and axion-like particles, or ALPs.
Axions. Didn't they come from particle physics theory for a different reason?
They did, initially. Axions were proposed to solve a specific problem in the theory of the strong nuclear force, something called the strong CP problem related to neutrons. But it turns out these hypothetical particles could also have the right properties, very light, very weakly interacting, to be cold, dark matter.
Interesting. So a solution to two problems potentially.
Potentially, yes. And then there are sterile neutrinos.
Sterile. Different from the regular neutrinos we talked about.
Yes, hypothetical cousins. They wouldn't interact via the weak nuclear force like regular neutrinos, only through gravity, making them even harder to detect.
There's a range of possibilities here. Some theories propose very light sterile neutrinos, just a few kilo-electron volts in mass. A team at Mainz University suggested these could annihilate in a two-step process, possibly explaining some puzzling X-ray signals seen from galaxy clusters.
Intriguing. But wouldn't light particles have that hot dark matter problem again?
Generally, yes, light-dark matter can be problematic for forming small galaxies. But this specific Mainz model suggests a production mechanism in the early universe that might allow them to act cooler than expected, potentially avoiding that issue. There are also ideas about much heavier sterile neutrinos, though again, their existence is purely theoretical right now.
It's astonishing how many different avenues scientists are exploring, and the names. I also saw something about HYPers, highly interactive particle relics. Ah, yes, H-wipers. That's a more recent idea, kind of a different angle.
How so?
This model suggests that maybe a specific kind of phase transition happened in the very early universe.
Like water freezing, but for the whole universe.
Sort of, yeah, a fundamental change in state. This transition might have temporarily, but significantly, amplify the interaction strength between dark matter and ordinary matter.
Okay.
This could allow for dark matter particles that are actually very, very light, much lighter than WIMPs, but still produced in the right abundance to account for the dark matter we observe gravitationally.
And why is that interesting?
Well, it could potentially explain why the WIMP searches haven't found anything. Yet, maybe they're looking in the wrong mass range. And it suggests that future detectors, perhaps designed differently, might be able to probe this very low mass range for these HY-parabers.
So we have this whole zoo of potential invisible suspects. WIMPs, axions, sterile neutrinos, H-wipers. It really highlights the breadth of the search. But is the idea of any kind of dark matter particle universally accepted? I feel like I've heard whispers of alternative theories challenging the whole idea.
That's a very important point. While the dark matter particle hypothesis is definitely the leading explanation within the mainstream cosmological community, there is indeed a level of, let's say, healthy skepticism. And there are alternate ideas being actively explored.
Okay.
One of the most well-known alternatives is MOND.
MOND. What's that stand for?
Modified Newtonian Dynamics. It was first proposed by Mordechai Milgram back in 1983.
Modified Newtonian Dynamics. So, changing Newton's laws.
Essentially, yes, but only under specific circumstances. The core idea of MOND is, instead of assuming there's unseen matter causing extra gravity, maybe our understanding of gravity itself is incomplete, particularly when you get to the incredibly weak gravitational accelerations found way out in the fringes of galaxies.
So gravity might behave differently where it's very weak.
That's the proposal.
Yeah.
MOND suggests a modification to Newton's familiar law of gravity that only becomes significant at these extremely low acceleration levels. Proponents argue this modification alone could potentially explain the flat rotation curves of galaxies without needing any dark matter at all.
Wow. Okay.
And there are related ideas too, like STVG, Scalar Tensor Vector Gravity, developed by John Moffat more recently, which also aims to explain galactic rotation, cluster masses, and lensing without invoking dark matter.
So instead of adding invisible stuff to the universe, they're suggesting we need to tweak the fundamental rules of the universe, specifically gravity on large scales. That sounds pretty radical.
It is a significant departure from the standard Lambda-CDM model, absolutely. And MOND has had some notable successes in explaining certain observations, particularly at the scale of individual galaxies. Furthermore, some researchers like Gerhard Hensler and Pavel Krupa have been quite vocal in pointing out apparent discrepancies between what the standard cold dark matter model predicts and what we actually observe on smaller scales.
Discrepancies like what?
Things like the number and distribution of small satellite galaxies orbiting big ones like our Milky Way and Andromeda. The standard model seems to predict more small satellites than we see, and their distribution is sometimes puzzling. These researchers sometimes talk about dark matter in crisis, suggesting CDM might not be the full story, and perhaps some dwarf galaxies form differently, maybe through tidal interactions.
It really sounds like there's an ongoing, lively debate happening. Are there any other recent challenges to the dark matter idea?
Well, interestingly, there was a study published in 2024.
Oh, very recent then.
Yes. It suggested that maybe some of the anomalies in galactic rotation curves, the very thing that kicked off a lot of this, could potentially be explained by carefully considering subtle effects within Einstein's existing theory of general relativity. Specifically, something called retarded gravitational potentials.
Retarded potentials, meaning gravity takes time to travel.
Exactly. Considering the time delay effects and gravity's influence within a complex rotating system like a galaxy. Using detailed data from a large galaxy survey called SPARC, they argued that these general relativistic effects, when properly accounted for, might explain the observed rotation curves without needing dark matter or modifying general relativity itself.
That's fascinating. So maybe we just need to be more careful with the physics we already have.
It's certainly a possibility that researchers are actively digging into. It highlights how complex these systems are. However, it's also really crucial to remember why the standard model, Lambda-CDM, which includes cold dark matter, is so widely accepted.
Why is that?
Because it's been remarkably successful at explaining a huge range of observations, especially in the larger scales. Things like the overall structure of the universe, the cosmic web of galaxies and clusters, and critically, the detailed patterns we see in the cosmic microwave background radiation, the echo of the Big Bang.
Ah, the CMB. That seems to be a really important test.
It is. Lambda-CDM provides an excellent fit to the CMB data. So while these alternatives and challenges are important and drive research forward, the overwhelming consensus in the scientific community currently still favors the Lambda-CDM model as the best overall description we have. But, as we've said, the fundamental nature of that C, the cold, dark matter, and indeed the lambda, the dark energy, which makes up an even bigger chunk of the universe, remains one of the biggest, most profound open questions in all of physics and cosmology. Some are even exploring if gravity's own self-interaction within general relativity could mimic MOND-like behavior on galactic scales, another potential path. The investigation is far from over.
This is all incredibly complex, but it really does highlight just how much we still have to learn about the universe we live in. This elusive dark matter seems absolutely fundamental to understanding, well, everything out there.
It really is.
Yeah.
If dark matter exists and has the properties we think it might, its nature has profound implications for the entire story of the universe, how it evolved, how galaxies like our own formed, how all the large-scale structures emerged, and even ultimately what the long-term fate of the cosmos might be.
When you put it that way, it's quite humbling to realize that something like 95% of the universe's total energy and matter content is in forms we don't really understand yet, this dark matter and the even more mysterious dark energy.
Absolutely. It's what keeps cosmologists up at night, but also what makes the field so exciting. The ongoing search for dark matter is a powerful testament to, humanity's deep-seated curiosity, our relentless drive to figure things out.
From those deep underground labs to the giant telescopes.
Exactly. From experiments probing the tiniest possible particle interactions deep beneath our feet to powerful telescopes peering across billions of light years, This continuous quest holds this incredible potential for truly groundbreaking discoveries. Discoveries that could completely revolutionize our understanding of cosmic origins, something we love exploring here on Cosmic Origins Revealed.
Well, this has been a truly deep dive into a fascinating and still very much open question here on Cosmic Origins Revealed. Just to quickly recap for everyone listening, we've explored the compelling evidence suggesting dark matter exists, from those weirdly fast-spinning galaxies and tightly bound clusters to the way light gets bent across the cosmos. We've also delved into the zoo of theoretical candidates, WIMPs, Axions, sterile neutrinos, maybe even H-wipers.
And we touched on those intriguing alternative perspectives like MOND that challenge the standard picture by suggesting maybe it's gravity itself we need to rethink.
Exactly. And as you've helped us understand today, the mystery of dark matter remains one of the most significant and exciting unsolved problems in modern cosmology. It really is a frontier of knowledge.
A frontier we'll definitely keep exploring with you here on Cosmic Origins Revealed.
Absolutely. And we encourage you, our listeners, to continue your own exploration of these, frankly, mind-bending topics. You can discover more in-depth discussions about the universe's greatest mysteries by visiting the Cosmic Origins Revealed website or subscribing to our feed so you don't miss any future deep dives with us.
And we would genuinely love to hear your thoughts. What do you think this elusive dark matter might be? A known particle behaving strangely, something totally new. A modification of gravity? Share your ideas, your questions with us on our social media channels. Your curiosity really does fuel our cosmic journey together here on Cosmic Origins Revealed.